Okay, ready to go. Have a good session.
Okay. Thank you. Okay, so this is the first session on multi-party computation, and myself and Vuxiang will be chairing the session. So we have 5 talks, and the first talk is on motive, almost free branching in GMW via vector scalar multiplication. And the paper is by David, Vladimir, and Stanislav. And Stan will give the talk. Okay, so let's start.
So thank you for the introduction. Can you see my screen?
Yes.
Okay, so my name is Stan Peseni, and this is a joint work with David and Vlad Kolesnikov, and I'll be presenting MOTIF, which stands for Minimizing Oblivious Transfers for Ifs. So in this work, I'll be discussing the GMW protocol, which is a foundational MPC protocol that represents the function to be evaluated as a Boolean circuit consisting of AND and XOR gates. Now, in GMW protocol, the communication in terms of both bandwidth and network latency is the bottleneck. We focus on bandwidth, which is expensive as a result of having to pre-compute oblivious transfers, which are used to evaluate the circuit's AND gates. In this work, we significantly reduce bandwidth by taking advantage of conditional branching, and that is in an if or a switch statement, we take advantage of the fact that only one of the branches is actually evaluated. It has been assumed that we need communication proportional to all branches in a conditional. We show that we need communication proportional only to a single branch. At a high level, we represent conditional branching as a vector scalar multiplication and demonstrate that we can do vector scalar multiplication for the same cost as a single AND gate. AND gates require the use of expensive and interactive primitives, and hence we first review costs associated with AND gates to motivate the need for efficient vector scalar multiplication. So in order to evaluate AND gates by 2 parties, we need to evaluate 2 terms interactively. Each of these terms is evaluated via 1 out of 2 oblivious transfers or short-lived OT. OTs are very expensive, and the cost of an AND thus corresponds to 2 OTs in the 2-party case. For P parties, P times P minus 1 OTs. In order to reduce the OT costs, GMW implementations use the efficient OT extension protocol. But despite this improvement, OTs consume OT extension matrix rows of size kappa, which is the computational security parameter. Thus, computing a 1-bit multiplication requires big O of kappa communication. We show that conditional branching can be efficiently achieved via vector scalar multiplication, and for that reason, we first demonstrate how vector scalar multiplication can be implemented efficiently. The naive approach for vector of size n would require n AND gates and thus n times p minus 1 OTs, and we can do much better than that. We introduce a natural generalization of the AND gate. We call it a versus gate, and a versus gate requires only p times p minus 1 OTs for vector of any size, just like one AND gate. The key idea is that instead of using n times p minus 1 OTs of 1-bit secrets, we use p times p minus 1 OTs of n-bit secrets, and this significantly reduces communications as we consume fewer kappa-bit long OT extension matrix rows. We demonstrate our versus gate on a vector of 2 bits and 2 players only. So for scalar A and vector BC, we can naively use 2 AND gates to get AB and AC. Instead, we replace the 2 AND gates by our versus gate, which takes the scalar A and vector BC as input and outputs AB and AC. And the key idea is that to evaluate all interactive terms, we follow the same steps as in the AND gate OT, except Bob's inputs are longer. And due to time constraints, I will refer you to our full presentation to see the details of a versus gate. And instead, I will now focus on how the versus gate is useful for conditional branching. So to show how versus gate facilitates efficient conditional branching, we first state our invariant. On each wire of each inactive branch, pairs will hold a share of 0. On the other hand, on each wire of the active branch, pairs hold valid shares. In our example, we have 2 branches. We consider the upper branch to be the taken, that is active branch. And now if our invariant holds, we can substitute each pair of AND gates across branches with a single versus gate. Recall that versus gates use the same number of OTs as a single AND gate. And thus, by making these substitutions, we drive down the cost of the overall circuit. So we substitute the first 2 highlighted AND gates with one versus gate, and also these 2 highlighted AND gates with another versus gate. So we have 2 AND gates that we want to substitute with a versus gate. As the AND gate on the top is active, the inputs to the top gate X and Y hold true values. The inputs A and B of the bottom AND gate equal 0. Now we construct the versus gate. We set the scalar to X XOR A. And by our invariant, 1 of XOR A is 0. Hence, this value always equals to the scalar on the active gate. The input vector then consists from the second inputs to the AND gates, Y and B. And we expect to get XY for the first output bit, as that is the output of the active gate, and 0 for the second output bit. So let's plug in 0 for A and B. Now let's simplify the expression. And we get the expected output XY on the active branch and 0 on the inactive branch. So versus gate maintains our invariant. So this was motif, and we are the first work to achieve significant conditional improvement in the multi-party setting. So thank you for listening, and I'm happy to take any questions.
Okay, thanks. Thanks, Stanislav. Are there any questions? We have time for a quick one question. Wuxian, are you looking at the Zulip?
Yeah, I also look at it. Yes, I could. There's no any question.
There's
question. Yes.
All right. So if not, then I will ask a quick question. So you have introduced new primitive gates, right? For instance, this scalar vector multiplication, right?
Yes. So basically, the versus gate can be perceived as another type of gate, but I stress that it really is a generalization of the AND gate. So the steps that you take to evaluate are similar, just the details during the evaluation. You're not doing OTs on 1-bit secrets, but instead of on longer secrets.
Right. So do you foresee some applications, some functions where having this kind of gate would reduce the number of total number of gates?
So yeah, so in our paper, we actually implemented the approach, and we did test it. So we, for example, ran it on a circuit that consists of string comparison. That's a suitable circuit for GMW because it's a shallow circuit, so it's not too deep. And just for some numbers, so we had for 16 branches, we got a communication improvement of 9.4. So there are a couple of reasons why it was not 16. So for example, the number of base OTs for the OT extension is the same. Then the communication in the online phase is the same. So the source of the improvement comes from the offline or the pre-computation. And also, there were some costs associated to padding, which were more implementation details.
Yes, great. I think there is another question, but we can take it offline. Is the code of motif available? I think you can answer that in the chat box. We are running out of time, so we will go to the next talk. But please the chat box. Okay.
Yeah. Good. Yeah.
Okay, so let's move on to the next talk. The next talk is on maliciously secure matrix multiplication with applications to private deep learning. And the paper is by Hao Chen, Miran Kim, Ilya Razenshtein, Dragos Rotaru, Yong-Soo Song, and Samir Wag. And Samir is going to give the talk. So over to you, Samir.
Thank you, Arpita, for the introduction. I'm just going to share the screen.
Yeah, all good. All
good?
Yeah.
Once again, thank you so much, Arpita, for the introduction. I'm going to be presenting this work, and as Arpita mentioned, like this is joint work with an excellent bunch of collaborators. So, and I think a lot of them are in the audience today, so feel free to ask them or me any questions about this. So this work is in the domain of, as the session says, in the domain of multi-party computation research. And multi-party computation refers to a set of parties who jointly want to compute a function. So each party has their own private input and they want to compute a joint function without really revealing their private input. The big part of like the interesting bit of this is usually in the world, like we have a centralized entity who is aggregating all this data and then just doing the function computation locally. However, the key insight here is we want to remove this centralized entity and just do this computation among the parties. One big sub problem in this domain is that of triple generation. So frequently when we want to compute an arbitrary function, we decompose it into additions and multiplications, and this triple is just a part of a pre-processing which will help you compute the multiplication part very, very efficiently. So in particular, in a triple generation protocol, we want to generate shares A, B, and C, like split between these parties, such that A times B is equal to C. Before I proceed into talking the details about this, I want to mention that this entire work is in the dishonest majority corruption model. So in particular, you could have all but one party be maliciously corrupted, and they could all be collaborating with each other to break the privacy, and we still want to be able to achieve guarantees in this setting. So let me talk about the central result of this work. So the overhead of triple generation in this line of work is generally prohibitive. In particular, it takes order n cube amount of communication to do private matrix multiplication or generating matrix triples in particular. In this work, what we show is you can actually do these matrix multiplication or just B-word triples, but of matrices in order n square communication. I'm presenting this for matrix multiplication. In general, this holds for bilinear triples, and some of the details I'll refer to the paper. So let's take a look at how we achieve this. So I'm going to present the state-of-the-art protocols in speeds, which is the framework we built on, and then also mention the delta or the changes we have to make over that to actually achieve some of this. So in speeds, what happens is all these parties locally generate their own randomness of AI and BI, and then they encrypt it using a public encryption scheme. The additive homomorphic property of the encryption scheme ensures that if you just add up these encrypted ciphertext locally or just together, then you get encryption of A, which will be the sum of each of the plain text in these encryptions, and similarly encryption of B. And then all these parties simply just broadcast these values of the encryption. So each party can locally compute encryption of A and encryption of B by just adding all these broadcasted messages together. And then the homomorphic multiplication property of the encryption scheme is used, where we can actually multiply these two ciphertexts to actually get a ciphertext C, which encrypts the product of A and B. And then the final step is a distributed decryption protocol, where you can actually get shares C1, C2, and Cn, which are actually the decryption of the ciphertext C. And as we know that C actually contains the product A and B. So this is roughly the overall schematic. There is a lot more detail to these protocols. In particular, we have the max associated with this, since we are in the dishonest majority model, as well as the details of the secret key being distributed among the parties. So I'm going to skip over that. I'm going to talk about the biggest change which happens effectively is instead of this, this multiplication in the center, which is a term-by-term product right now, we change it into a matrix product where each of these values, AI and BI, are actually matrices of a particular size. And then when you do this product, we actually try to compute a matrix product and in effect generate a matrix triple. The second part of this is the dishonest majority part, that each party can actually use incorrect inputs or lie about the noise in the plain text, which would corrupt the encryption scheme or which could also have consequences in the distributed decryption protocol. And we want to be able to defend against all of this. And that's where we use zero knowledge proof similar to prior art. So I'm going to talk about this in just a minute, but to quickly summarize the details in here. First is that we actually demonstrate how to do matrix multiplication over ciphertext for arbitrary size matrices. So it's not immediately obvious that if instead we replace the term-by-term product with a matrix product, we can actually change the asymptotic complexity of these protocols. So that's the first contribution here. And the second one is the elimination of sacrifice using a larger depth homomorphic encryption scheme. And we demonstrate that using this larger depth homomorphic encryption scheme, along with the elimination of sacrifice, actually ends up with a more promising protocol than using lower depth HE. So quick detail about the zero knowledge proof. It's very similar to prior work. We actually, this is the setup where each party just broadcasts their own encrypted value. And we use a standard Sigma protocol, which runs in 3 phases. So the commitment phase is really just this, that each party broadcasts their value and they have already committed to an encrypted value. The second step is the challenge phase, where we use an n-party zero knowledge protocol. And so each party is simultaneously a prover and verifier in this entire computation. So the challenge is actually generated by all these parties simultaneously. And finally, the verification on a response mechanism is where the parties reveal certain values and then do some verifications locally. And if it succeeds, proceed with the protocol. The biggest changes here are, first, we demonstrate that all these protocols actually work with BFV as the underlying homomorphic encryption scheme, whereas prior work used BGP. The second advantage is that BFV can be used in specific parameter regimes, which enable us to reduce the communication overhead of the zero knowledge proof and also simplify the proofs in some ways. So that's the core details of the paper at a very high level. I think with that, I'm going to present just one experimental result. So this is just a table straight from the paper, and I'm actually going to gloss over this and just focus on these 4 specific values. So what this table shows here is the top table shows the timings in the LAN setting, in a local area network setting. The bottom table is in the WAN setting. And the numbers on the right are prior state of the art, which is the speed state of the art. And then the numbers on the left are implementation. And they are all for 16 cores. So in parallelizing using 16 cores. And finally, these are timings for about 1,000 by 1,000 size matrix. So the first result here is we are definitely faster than prior work, in particular in the LAN setting, about 3.6 times faster, in the WAN setting, about 36 times faster. The second important result here is that since it's an asymptotic improvement, if we increase the matrix sizes, these improvements just become more impressive. The second result which I want to highlight here is really the comparison between LAN and WAN. So for instance, if you look at prior work, the difference between LAN and WAN is 11 times, whereas for us it's only 13%, which is a very small improvement. And what this really hints at is the fact that our protocol is very much compute bound, as opposed to communication bound, which is what most of MPC is. And the reason why this is interesting is because with communication, there is a fundamental limit. Like if we have to send certain amount of data over the internet, there is a minimum amount of overhead we have to pay. Whereas if it is compute bound, there is hope of using better hardware, parallelizing it more and making it more efficient. So that's another interesting sort of result here. With that, I'm going to just quickly mention the details of like the matrix multiplication, the ciphertext matrix multiplication. Here we use this prior work from CCS 2018, which actually takes a matrix product and very optimally transform it into things which are homomorphic encryption friendly. So in particular, it converts it into dot products or term by term products, and also additions, and the term by term products include some rotations. And so in particular, they make it very, very HE friendly. There are also a few other optimizations and system challenges we solve in this process, and these are expressed more in detail in the paper, but I just wanted to quickly mention that. And in particular, the last one is really showing that whenever you use a homomorphic encryption scheme, you have a finite size or a certain size of this modulus, but how do we actually scale to arbitrary size matrices? And so these are just some techniques mentioned in the paper. The entire version of the talk actually contains some future work as well, but I think for this, I'm just going to stop here. Just mention briefly these two future work slides. That it's interesting question, open question to actually look at extending this to rings, as opposed to this work is purely in the domain of fields. And the other question would be to do silent matrix triple generation. So using this entire emerging line of work of silent preprocessing to actually apply it to this work. With that, I would like to thank you for your attention. The paper is up online, and I think a lot of the co-authors are also in the audience, so feel free to ask any questions to me or any of them. Thank you.
Thank you, Samir. Okay, we can take a very quick question. Let me see.
Yeah.
Okay, Pratik, do you want to ask, or so Samir already showed some tables, right?
That's okay.
Do you still have a question?
No.
Okay.
Yeah, thank you.
Okay. Okay, so I think with that, we will move to the next talk, because we are running out of time. Maybe in the end, if we have more time, then we will. I have some question for you, Samir. I will do that.
Yeah, thank you. Sorry for running over time.
No, you are fine. Okay, so let's move on to the next talk. Beautiful title. Okay, so the next talk is on secure MPC. Laziness leads to God. And the paper is by Sai Krishna, Badrinarayanan, Ayush Jain, Nathan Manohar, and Amit Sahai. And Nathan is going to give the talk. Okay, over to you, Nathan.
Okay, thanks for the introduction. Can you see my slides?
Yes, everything is good.
Okay, cool. Okay, so in secure multi-party computation, there are many parties, each possessing some private input, and they wish to compute some joint function f on their private inputs. And to do this, the parties execute a protocol, and afterwards, each party should only learn f on their private inputs. Now, in traditional MPC, if a party aborts during the execution of the protocol, they are treated as a corrupted party that is colluding with other parties. However, in many situations, this is unrealistic. Traditional MPC views an aborting party as some malicious entity that is colluding with all other aborting parties and other corrupted parties, when what can actually happen in reality is that like the power line collapsed and the user lost connectivity, and that's why they stopped responding. So in this scenario, an aborting party is most certainly not a mastermind colluding with the other parties. So to model this scenario, we like to consider MPC where we allow honest parties to abort. Honest parties may abort for a variety of reasons. So connectivity is one that we already went over. An honest party may simply lack the computational resources to carry out the computation in a certain round and be forced to abort. Or they may simply lose interest at some point in the protocol and stop responding. However, if their input is valuable to the execution of the protocol, we would not want their input to be discarded if at all possible. So motivated by this, we dealt with this model that we called Lazy MPC in this paper. So how should we go about modeling this? Well, in traditional MPC, there are honest parties and corrupted parties. And in lazy MPC, we're going to have a third type of party, which we're calling lazy parties, or honest parties that abort. And so in this work, we're going to focus on MPC protocols in the standard broadcast model. And the honest behavior of a party is now to just send the message honestly or abort in any round. And we're also going to assume that a party that aborts in some round never returns. And so in lazy MPC, the protocol is going to consist of two phases, an input commitment phase and then a computation phase. And so the input commitment phase is the first few rounds of the protocol. And this is going to be independent of the function. And this will be useful because it will allow us to reuse the computation phase with many different functions without having to redo the input commitment phase. And we're going to say parties that have completed this phase have successfully committed to their inputs. And then there's the computation phase. And in the computation phase, these rounds of the protocol, the parties will evaluate the function on the inputs that have been committed. So even if a party aborts during the computation phase, we still will evaluate the function on the input that it committed if it completed the input commitment phase. And we call this property input fidelity in our paper. And then we also want, if enough parties remain at the end, that is, a certain number of parties at least completed the protocol without aborting, all parties, including those that aborted, should recover the output. And this is guaranteed output delivery or God. And to model security, we dealt with threshold mixed adversaries. So these were formally introduced by Fitzy et al. In a couple of works. And a threshold mixed adversary is parameterized by a tuple of thresholds. And these correspond to the number of malicious, semi-honest, and fail corruptions the adversary can make. And fail corruptions correspond exactly to our honest aborting parties. They are parties that the adversary gets to specify when to abort, but does not learn any internal state information of the party. And Hurt et al. Showed in a work that guaranteed output delivery is only possible if this inequality holds. And so this will be the focus of our work. We'll focus on settings of thresholds where guaranteed output delivery is possible. Okay, so what did we show? We gave a 3-round MPC protocol with guaranteed output delivery in the plain model from learning with errors for all thresholds for which guaranteed output delivery is possible. And to do this, we used two tools. We introduced a new primitive that we call threshold multi-key FHE, and we built it in the plain model from LWE. And we also built multi-string NISX in the plain model from LWE. And so what are some of the properties of our protocol? So one nice property is that the communication complexity of the protocol is proportional to the depth of the circuit evaluated, and not like only the depth, not the circuit size. And so the first 2 rounds of our protocol serve as the input commitment phase, and the final round serves as the computation phase. Moreover, the final round can be repeated as many times, polynomially many times with different functions, and can be reused. We have input fidelity, which we already went over. Moreover, our 3-round protocol is round optimal because due to a lower bound of Gordon et al. That showed that it's impossible to have guaranteed output delivery in 2 rounds, even with the CRS. And moreover, if you instantiate the threshold mixed adversary with a standard adversary that only has malicious corruptions, our protocol immediately implies a round optimal, maliciously secure protocol with guaranteed output delivery in the plain model from learning with errors. And previously, Gordon et al. Had shown it in the CRS model, and an independent work of Nunt et al. Showed it from the incomparable assumption of public key encryption in ZAPs using completely different techniques from ours. And for the techniques we use, I'll defer you to the full presentation. Thank you.
Okay, thank you, Nathan. Are there any questions? Are there any questions for Nathan?
Okay.
Huxian,
Yeah.
do you read something in Zulip?
No question
No?
from Tulip. Yeah.
Okay, so I have some question for you in that case. So I have actually several questions. So let me ask one, and let's save the others for the end of the session. So you mentioned that this model was first introduced in a paper by Hart et al., right?
Fitzy et al., but Hurt was also one of the authors.
Right. Yeah. So I guess in that work they have presented an information theoretic construction. Is that right?
Yes, I believe they had, and they had also shown lower bounds, basically showing when certain things are possible or not. And I think they had given a computational construction, but I believe the results were just like maybe polynomial number of rounds or constant number of rounds for some constant. The round complexity, like under computational assumptions, had not been like extensively studied in that work.
Okay, but I think there is another primary difference is in terms of the network assumption. So I guess they assume pairwise private channel model between.
Yeah, so they
parties,
also sometimes considered, I don't remember exactly what that work considered, but I know some of the works also allowed point-to-point channels in addition to broadcast and various things. And yeah.
All right. Whereas your work is on broadcast.
Only broadcast. Yeah, we don't allow point-to-point channels at all.
Right. So I don't think information theoretic is possible. All right.
Yeah, I'm not sure.
So do you need a CRS? You do.
We don't need a CRS
No.
for any of our results. Yeah. And so the reason we can get around that is we use this multi-string NIZK. And we use the fact that our protocol happens to have the property that the entire first round is just everyone submitting random, like completely random information. That is like
right.
So then we can use that, also concatenate a CRS, and then use the NIZK for rounds 2 and 3. And that's how we are able to do this without do it in the plain model.
Right. So this multi-string NIZK is already introduced by somebody, I guess.
This was introduced by Groth and Ostrovsky, but we did it for the first time from LWE.
I see.
Yeah.
And the assumptions you think already they are tight, or there is a possibility of improving?
I mean, we only need LWE, and then we're using FHE and all these tools. So I don't know how to I mean, you could use the Ananth et al. Is a result using a completely different technique, but our techniques you would need to assume LWE. At least
is that just FHE or multi-key FHE?
No, we need this threshold multi-key FHE.
Right. So this is stronger than FHE. Yeah.
It's stronger than FHE, and yeah, we use a multi-key. Well, the way we build it is we use the multi-key FHE of BHP 17 along with threshold FHE of Bonnet et al. And we sort of show that these can work together nicely to give us what we need. We sort of need a multi-key FHE structure to do secure multi-party computation, but we need a threshold property to make it so you don't need all parties to remain online in order to
decrypt. Yeah. Okay. Yeah. Thanks, Nathan.
Yeah, no problem.
Yeah. So I guess you have a question, Nathan, in the chat window. Please answer to that when you get time.
Is it on Zoom or is it somewhere else?
In Zoom,
No,
here.
It's Zoom. Yeah.
Oh, I see it. Yeah. Okay.
Right. Okay. So the next talk is on towards efficiency preserving round compression in MPC. Do fewer rounds mean more computation? This is authored by Pramanjan Ananth, Arka Rai Chaudhuri, Arusi Goyal, and Abhishek Jain. And Arka is going to give the talk. Over to you, Arka.
Thanks, Arpita. Can you hear me okay and see the slides?
Yes, all good.
All right, awesome. Thanks. So today I want to talk about the efficiency preserving round compression compilers in MPC, or alternatively, do fewer rounds mean more computation? And as Arpita already mentioned, this is joint work with Prabhanjan, Arushi, and Abhishek. So you've already seen, this session about MPC, where MPC essentially allows parties that have some private inputs to jointly compute a function over their inputs. They do so by running a protocol, which involves exchanging messages, at the end of which all of them have the output. One of the parameters that we care about in this work is the round of this protocol, which simply constitutes of every participant sending a message. And for efficiency purposes, we want to actually minimize the number of rounds of interaction. So you also require some additional security properties, which roughly says that you don't learn anything beyond the output of the function. We've also seen MPC comes in various flavors, and we've seen some different flavors in prior talks. So what we consider is the setting where an honest majority of a majority of the participants are honest, and we only consider security against adversaries that are computationally bounded. Okay, so what do we know about round complexity in this setting? And actually, it's sort of quite well understood, and this is really exciting recent line of work, which established 2 round protocols in the honest majority setting and from minimal assumptions. So at a very high level, all of these works rely on this following sort of round collapse methodology, where you start with a multi-round protocol that computes F. It can be like anything larger than 2. Can be a polynomially many number of rounds, and over sort of these to get it down to 2 rounds. In these 2 rounds, you essentially run a protocol where you exchange information, and additionally, more importantly, you exchange garbled circuits. And the role of the garbled circuits is to essentially act as proxies for the parties in this larger multi-round protocol. What do I mean by that? So at the end of the second round, each party sort of locally and individually can emulate this multi-round protocol. Obviously, they can't interact anymore. So instead, these garbled circuits act as stand-in for the parties and do the computation for them. So, even though there is actually a multi-round protocol that's run, it's all done locally, and this is sort of provided for in the first round. This is a very high-level idea. There are lots of details that I'm sort of brushing under the rug. So what about the costs of these compressed protocols? As you can see, sort of the communication or computation sort of depends on what we start off with, the underlying protocol. So if specifically if we start off with some protocol which has total computational work W, which is a function of the number of parties N and the size of the circuit computing, this function that you care about. Then these 2 round protocols have a total communication or per party computation of at least O tilde N square times W, where O tilde hides polylog factors in the number of parties and security parameter. So the question that we really ask in this work is, can we construct efficiency preserving round compression compilers where we really talk about efficiency in terms of the total communication or per party computation? And our results are that actually, yes, in the semi-honest setting, where the adversary follows the protocol, we actually get a 2 round protocol where we sort of move the overhead from the multiplicative to the additive. And in fact, also the work now depends only polylog is a function of the polylog of the number of parties rather than on the number of parties itself. And in the malicious setting, we get a 3 round protocol, not a 2 round protocol, where the additive overhead is slightly larger, but there's no multiplicative overhead. So how does it sort of really stack up against prior work? So if you actually instantiate prior work with sort of the best known MPC protocols, say protocols that achieve total work roughly O tilde the circuit size, then prior work even in the semi-honest setting, you get an N square multiplicative overhead, and the additive factor is also like reasonably large, N cube. So in our work, we actually don't get this multiplicative factor, and the additive factor is not too far off from previous work. And similarly for the malicious setting, although I should note that the malicious setting in prior work is really 2 rounds, and our work actually requires 3 round protocols. So I've really talked about total communication and per party computation, and you can ask me, oh, what about total computation? So you can actually get total computation to match the total communication, which is this value that you see on the slides, but with the cost of an additional round. So if you're willing to have an additional round, you can actually get the total computation also to be brought down to be quite low. So a very natural idea, which is followed by a bunch of works, is to do this delegation of computation, where you elect a small committee of servers that is actually going to do all of the heavy computation, and thereby you sort of really save on the computation. And so our main idea in this work is actually to do this in a round efficient manner using just minimal assumptions and the tools that we have. Specifically, we managed to do this in 2 rounds in the semi-honest setting and 3 rounds in the malicious setting. So that's all I'll have actually time for in the short talk. I urge you to look at the long talk, or the paper is also up on ePrint, and I'd be happy to take any questions now.
Thank you, Arka. Yeah, no, that's not a question for you.
Yeah.
So I have a question if nobody is asking. I think I
Sure.
missed it. Is it honest majority or dishonest majority?
Honest majority.
I see. Okay. Okay. So do you think if we directly try to get an implementation of, so I guess you have tried to implement a degree 2 function because you have been, or degree 3 function.
So degree 2 essentially. So yeah, the multi-party degree is 2. Yes.
MPRE.
Yeah. Yeah. MPRE is 2.
Right, but it is still going via the round collapsing compiler.
Right. So yeah. So you can think of like the existing compiler as the protocol that you have it, but you run it among very small set of parties. So these are parties that are doing sort of running existing compilers, but you need to do a lot of to be able to compress it. You need to be able to provide enough information to these parties to actually run the protocol, because in the first round you don't even know who the committee members are going to be. And so for that, you need some helper protocols. And these helper protocols actually turn out to be, again, of MPRE degree 2. And these are sort of low cost helper protocols, and you can actually sort of put them all together and make it work.
Right. So in this year's TCC, there is a paper by Lin. So they have bypassed the, did you, I mean, of course,
yeah, so they don't use a round compression compiler as you're pointing out, but the overhead is still like n square because they do have to actually communicate roughly n square communication per gate, even though it's not the round compression. But I don't know, like you can actually start off with their protocol and do the same thing, but yeah, their protocol also does actually suffer from this kind of thing, but we didn't actually look at that before we did this work, of course. So yeah.
Okay. So okay. So that would be a nice open question. I mean, do you think there can be an improvement if, in the smaller committee to which you are delegating the computation, if you can do Lin's work, I mean, if you can plug in their method.
So in the semi-honest, and this is in the semi-honest setting specifically. Right. At least without correlated randomness. But yeah, in terms of semi-honest, I don't see any too much that could be improved. In the malicious setting, ours is a 3-round protocol. In the plain model, we do have some results in the in some CRS, some reference string model and so on. But yeah, 2 rounds is potentially open. We don't know if it's possible to do it with this kind of complexity in 2 rounds. That's still open for the malicious setting at least.
Okay, I think that's all from my side. In Zulip, there is no questions, right, Bhukshan?
No from Zulip.
Okay, so then we will move on to the next talk. Thank you, Arka. Okay, so the last talk of the session is on efficient and round optimal oblivious transfer and commitment with adaptive security, authored by Communicati, Pratik Sarkar, and Xiao Wang. And Pratik is going to speak. Over to you, Pratik. It's all good. We can see your slides.
You're muted and you should turn on your camera.
Yeah, hi. Can you hear me? Yeah, good.
Yeah.
Thank you for the introduction. Hi, my name is Pratik, and today I'll be presenting our work on efficient and round optimal oblivious transfer and commitment scheme with adaptive security. This is a joint work with Communicati from Boston University and Xiao Wang from Northwestern University. Today I'll talk about MPC primitives. Since MPC has already been defined, I will directly go into the definition of the primitives. Oblivious transfer is the two-party primitives. There is a receiver who has an input choice bit B, and there is a sender who has two messages, M0 and M1. The receiver gets MB as output. This is a fundamental primitive since OT is known to be complete for MPC, and it has also widespread applications in generic MPC, private set intersection, and zero knowledge. OT security ensures that a corrupt receiver should not know the other message M1 minus B, and a corrupt sender should not know the choice bit B. We consider the UC security model of Communicati. A corrupt receiver's input bit can be extracted by a simulator. Similarly, a corrupt sender's input messages can be extracted. We consider different corruption models. Static corruption considers whether parties are corrupt at the start of the protocol. We also consider different types of adaptive corruptions, where a party can corrupt it during or after the protocol. I will also describe a non-interactive commitment scheme. In the commit phase, the committer commits to his input M as a commitment C using randomness alpha. In the decommitment phase, the committer sends alpha as the opening. The verifier tries to reconstruct and accepts if the reconstruction succeeds. The commitment should be hiding and binding. In addition, the commitment should be extractable. That is, the committed message can be extracted from a maliciously generated commitment. Also, the commitment should be equivocal. That is, if the verifier is corrupt, a simulator should be able to commit to a junk message and later open to any valid message. In this definition, equivocal property ensures security against adaptive corruption of committer. Now I will present our contributions. Our protocols are UC secure to allow seamless composition into bigger protocols. All our protocols are round optimal and they are based on DDH assumption. We obtained the first adaptively secure non-interactive string commitment. Previous non-interactive schemes were bit commitments and required common reference string model, whereas our scheme works in the common random string model. Next, I will talk about our OT protocols. In the CRS model, we consider an OT protocol where the receiver can get adaptively corrupted and the sender can get statically corrupted. Such an OT protocol is called receiver adaptively secure OT. We obtained the first receiver adaptively secure OT, which has constant exponentiation over it. Next, we obtained the first adaptively secure bit OT with constant number of exponentiations. We also obtained results which are of practical interest. In the CRS model, we obtained the most efficient static OT with 8 exponentiations. PVW requires 11 exponentiations instead. We also obtained the most efficient static OT in the global random oracle model, which requires only 5 exponentiations per OT. The recent work by Masny and Rindal obtained similar efficiency, but they are from interactive DDH, which is not known to be reducible to standard DDH. Finally, we combine our commitment scheme and adaptively secure OT to obtain a round optimal adaptively secure MPC protocol in the common random string model. Moreover, we show that the size of the setup string depends only on the security parameter and not on the number of participating parties. Now, I will briefly discuss our commitment scheme. It is inspired from the dual mode commitment scheme of Lindell. The CRS consists of 4 group elements. The committer commits to his input M using randomness alpha, and he reveals alpha as the opening randomness. I will not get into the specific construction. Instead, I will just discuss some of his properties which suffice for our construction. Lindell showed that the commitment is perfectly binding and extractable if the CRS is a non-DDH tuple. That is, G, H, T, and F is a non-DDH tuple here. The commitment is also perfectly hiding and equivocal if the CRS is a DDH tuple. And the 2 modes of the CRS are indistinguishable due to the DDH assumption. However, the mode of the commitment is programmed in Lindell's paper by programming the CRS, and that hampers adaptive security. We build our commitment scheme where the mode of the commitment can be set during the protocol execution. Instead of putting F in the CRS here, we require the committer to sample a F and send it along with the commitment. When the committer is corrupt, we are ensured from the CDH assumption that the commitment is extractable. That is, this tuple is a non-DDH tuple. When the verifier is corrupt, the simulator can construct the tuple as a DDH tuple here using the discrete log of T, and this yields the commitment in the equivocal mode and guarantees adaptive security. Finally, the honestly generated tuple is indistinguishable from the simulated tuple due to DDH assumption. I would also like to denote that the message M can be polylog kappa bits, yielding a string commitment. Now I will just briefly discuss the OT protocols. We use the commitment scheme to build our OT protocols. We build a receiver adaptive OT, where the receiver's OT message is a commitment to his bit. We add a sender algorithm where the sender encrypts his input messages in a way such that the receiver can decrypt the message corresponding to the committed bit. Okay, and receiver adaptive security follows from the adaptive security of the commitment scheme. By optimizing our previous protocols, we can obtain our efficient protocols, and we can obtain a semi-adaptive OT by considering bit inputs for the sender in the previous construction of the receiver adaptive OT's construction. Finally, we obtain full adaptive security by considering the BLPV transformation, which transforms any semi-adaptive OT to adaptive OT using augmented NC. And the augmented NC can be instantiated from DDH. So finally, I would like to conclude. We also obtain a 2-round adaptively secure MPC protocol. In the short CRS model, we also show that the first message of a 2-round receiver adaptively secure OT is an adaptively secure commitment. Our work improves the efficiency of round optimal UCOTs and make them practical under standard assumptions like DDH. It would be interesting to see if the efficiency can be further improved. Thank you. And yeah, that's all.
Yeah, thank you, Pratik. Let's see if there are questions for you. No. Okay, so I'll probably ask a quick question. So both the commitment and the OTs are UC secure, right?
Right. Everything here is UC secure.
And the commitment is non-interactive or interactive?
The commitment is non-interactive, and the OTs are 2-round protocols.
Okay. Okay, so that brings us to the end of the session, and let's